What do plants do? We mostly think of them as just sitting there. But of course, over time, plants grow, and they do have patterns of how they grow. And often plants are growing in a particular direction. This is known as tropism, some sort of directional response to a cue. Common things include growing towards or away from, say, light, gravity, touch. All of these can stimulate patterns in plant growth. These happen in response to various hormones that tell the plant when it's encountering something. Once a plant has grown some way, it can't undo it. It's going to be like that. This may be positive or negative. It might grow towards something or away from something. For example, touch, thigmotropism is the term for that. Vines are positively thigmotropic. They grow, if they touch something, they'll grow to grow around it to help hold themselves up. Here's an example of phototropism. The top of this plant here is bending towards the light. Come towards the light. That would be positive phototropism. Of course, roots often show negative phototropism. Gravitropism, growing either towards or away from gravity. Of course, our stems are usually negative gravitropic, growing up. Roots typically positively gravitropic, growing down. Root cap cells have little bits of starch that can move around. They'll move down due to gravity. That tells the plant that way's down. If you take a little seedling, let it grow for a bit, and then turn it sideways, then the stem will bend up, the root will bend down. Sometimes you'll see a tree where it's growing, it's got a bend in it. Something happened to tilt the tree. If it's on the side of a hill, that probably means that part of the hill slid down, tilting the tree, which means that's a place that can have landslides, which means that's a place you don't want your house. Something to look out for. Hormones are chemicals secreted by part of a multicellular organism that are released to travel through the body and signal parts of it to respond in various ways. Plants have several types of hormones. As is typical of hormones, responses are complex. Different cells will respond to the same hormone in different ways, or even one cell at different times of growth may respond in different ways. Several different big categories of plant hormones exist. One that you can see often if you've got plants that have been trimmed is the phenomenon of apical dominance. The apical meristem, the top growing bit of a plant, sends hormones that say, I'm the top. The rest of you, you're not, you don't need to grow as much. I'm the top part, getting highest up to get more light. Now, some plants do that more, some less. Well, what happens, say, if you've got a bush or tree and you come in and chop off the top bit, if it's not a monocot, typically you've got side buds then that start to grow up more. So you get a more broad, bushy shape to your plant if you've trimmed the top. You just cut off what was saying, I'm the top, so there's no apex to dominate, and the other parts will grow out more. Here's another example. Ethylene. It's a very simple compound, 2 carbons, 4 hydrogens, and double bond with the carbons. It's actually a very important plant hormone, though. One of the things it does is help to tell fruit to turn ripe. This is taken advantage of in the grocery industry, you can pick green fruit on a farm, which is harder, less likely to get beat up when you ship it somewhere. And then once you've gotten it to the store, you can add ethylene, and that green fruit, like the tomatoes here, will ripen. They often still don't taste great, but look prettier at any rate. Similarly, if you get some fruit at the grocery, say, and find that it's not quite ripe, if you stick it in a bag with an apple or two, that will often help it to ripen up quite a bit. Apples not only ripen with ethylene, they produce quite a lot of ethylene as they ripen, and so that extra ethylene made by the apple works well to make other things turn ripe. Conversely, if you've got something that's already ripe, you don't want to stick it in with an apple, because that will tend to make it get even riper. One important thing that plants need to coordinate with hormones is when it's time to make a flower. Of course, different plants flower at different times. So each one has its own particular cues that it's using to know when to flower. One common clue used is how much daylight versus darkness. Through the year, we go through, in winter the days are shorter, the nights are longer. In summer the days are longer, the nights are shorter. And so we go through this cycle, if you're not too close to the equator when there's not much difference. And plants can detect this and use that as a clue. So we have plants that may respond to shorter days. If the night's getting longer, the plant recognizes that and, okay, it's time to flower. Say that will be good for something that likes to flower in the fall. Long day plants will flower when the night is shorter. Something flowers in the spring, say. Intermediate day plants, night's not too long, not too short. Those could perhaps flower both in spring and fall. Of course, there are plants that don't care how long the day or night is. They're depending on something else. Many organisms have both kind of an internal timer, a biological clock, that gives it roughly a 1 day circadian rhythm pattern. But it's not perfect as a clock, and so encounter with light is a key thing to help keep that in sync. So the combination of the internal rough clock plus the stimulus of light helps the plant tell what time it is, and that affects what the plant is doing. Does it open the stomata? Does it close them? Is it time to open or close the flowers? Things like that. Animals have these features too. This is, for example, why we have problems with jet lag. We've got our internal clock, and then we go someplace else, and our internal clock's not right, and we have to adjust. Similarly, this is part of why there are problems if you get too much light late into night. You tend to not sleep well. Say if you're looking at your phone late, all that light to your eyes makes you think it's still daytime, and that can cause problems. Here's an example. Here's a bee. Noon versus midnight. Noon, catch all that sunshine, stick out. Nighttime, droop down. Of course, in the morning, sunlight starts going to be more sideways before the sun gets high in the sky. So the leaf is positioned ready for that. Plants, roots, just sitting there, they're relatively vulnerable. It's easier for an animal to come along and start eating it. But plants do have a variety of defenses. One is an immune response known as the hypersensitive response. If a plant detects it's under attack, say insects are munching on it, or perhaps It detects a fungus or some sort of disease. The hypersensitive response seals off that area, lets it die. Kind of like the idea of amputating a leg that's got a serious infection that might spread to the rest of the body. So, for example, these brown spots on the oak leaf, something's been attacking the leaf, and it's blocked those off. Those parts are going to die. And of course, if there's some fungus in that part, that's not great for the disease to have the part that it's in die and dry up. Also, not only does that bit die, it sends signals to the rest of the plant saying, look out, you're being attacked by, say, a fungus or insect, whatever it is. And this leads to other chemical adjustments in the plant to respond. In addition, some of these chemicals go out in the air. Nearby plants may detect it and start to put on their defenses as well. And there are also predators that can detect these smells. Say a predatory insect, hey, it smells like that tree over there is getting munched by some yummy caterpillars. Let's fly over there and eat them. Just what the plant wants, not what the caterpillar wants. So you have that as a part of the defense as well.